This image shows two early smartphones, the precursors to devices that now define modern life. Inside a contemporary processor, engineers have packed tens of billions of individual transistors onto a single silicon chip. A transistor functions as an ultra-fast electronic switch. It regulates the flow of current without relying on any moving mechanical parts. These microscopic switches operate at a scale that defies intuition, flashing between on and off states billions of times every second. Understanding this mechanism requires us to first master the electrical properties of silicon. To understand the limits of this technology, we must confront the laws of quantum physics. Digital civilization is built upon our ability to manipulate the physical laws governing a switch the size of a few atoms. The engineering of the transistor begins at the atomic level. We have to look at why we rely on pure silicon rather than highly conductive metals like copper. Electrons within a solid material are restricted to specific allowed energy ranges, known as energy bands. The valence band contains bound electrons. The conduction band allows free movement. The space between is the band gap. Conductors overlap. Insulators have massive gaps. Silicon is a semiconductor with a moderate 1.1 electron-volt gap. Thermal energy kicks some electrons across into the conduction band. When an electron leaves the valence band, it creates a vacancy called a hole. These holes behave as positive charge carriers and contribute to the overall conductivity of the material. Silicon's moderate band gap allows its conductivity to be precisely controlled, providing a stable foundation for modern electronics. While silicon is a capable semiconductor, pure intrinsic silicon doesn't conduct enough electricity to power computers. Engineers improve this using a process called doping, introducing specific impurities into the silicon lattice. Adding atoms with 5 valence electrons, like phosphorus, creates N-type silicon. It bonds with the lattice, leaving one extra unbonded electron free to move. In these N-type materials, negatively charged electrons serve as the majority charge carriers. Introducing atoms with 3 valence electrons, like boron, creates P-type silicon. This forms a structural deficit of electrons. In P-type materials, these empty spaces, or holes, act as positive majority carriers. A hole behaves as a real, mathematically quantifiable positive particle within the crystal lattice, moving through the structure with its distinct charge and mass. Doping provides us with 2 building blocks, one with an excess of negative charge and one with an excess of positive holes. The next step is to physically combine an N-type block and a P-type block into a single solid piece of silicon. This diagram shows the p-n junction, where these materials meet. Upon contact, electrons and holes diffuse across the junction to combine, driven by the concentration gradient. Neutralizing leaves behind fixed, statically charged ions locked into the crystal. These form the depletion region, a physical barrier zone where no free charge carriers can exist. This region creates an internal electric field that eventually becomes strong enough to stop any further movement of charge across the boundary. In reverse bias, a battery pulls charge carriers away, widening the depletion region into an impassable wall. Flipping to forward bias forces carriers toward the junction, narrowing the region until current flows freely. This mechanism acts as an electrical valve, controlling the flow of electricity based entirely on the applied voltage. The p-n junction allows us to direct or halt electricity without the need for mechanical switches. Engineers evolved the p-n junction into the definitive switch of the modern era, the MOSFET. This is the anatomy of a MOSFET, featuring a source, drain, and gate, with an ultra-thin insulating layer of silicon oxide. In the gate-off state, the depletion regions naturally block the flow of current. This non-conducting state represents a binary 0. When we apply voltage to the gate, it generates an electric field passing through the insulating oxide layer. This field attracts charge carriers to the surface, forming a conductive bridge that allows current to travel from source to drain. With current flowing through the channel, the switch represents a binary 1. Modern processors execute complex logic by selectively inducing billions of these conductive channels using electric fields, flashing on and off across the chip. To increase computing power, engineers have spent decades shrinking these MOSFET components to fit more onto every chip. Transistors in modern processors have dimensions that measure just a few nanometers across. At this scale, the components are approaching the same dimensions as the de Broglie wavelength of the electrons themselves. Because the electron's wave nature becomes comparable to the size of the transistor, the classical particle-based physics of the p-n junction model no longer accurately predicts their behavior. This introduces wave-particle duality. Electrons at these distances stop behaving like discrete particles and begin exhibiting the traits of oscillating waves. In quantum mechanics, an electron's position is defined as a cloud of probability rather than a single fixed coordinate. Modern chip design has evolved into a struggle against this probabilistic behavior, where subatomic wave mechanics replace the predictable flow of classical electronics. This struggle is most evident at the MOSFET's insulating gate oxide, which is now only a few atoms thick. Quantum tunneling occurs when the electron's probability wave becomes wider than the physical insulating barrier. The electron can spontaneously pass through the solid wall. Electrons can now leak across the closed switch, even when the gate voltage is turned off. This results in uncontrollable leakage currents, generating excessive heat and draining battery life. Engineers are fighting back by moving toward 3D transistor designs that wrap around the channel to better contain these leaking electrons. Classical solid-state physics enabled the smartphone revolution, but mastering quantum mechanics is now the prerequisite for the next generation of computing hardware.